Hello everyone. We're going to start off by just looking at the AP practice problem answers that I posted yesterday or that I assigned yesterday. So I will have a solutions video posted for tomorrow going over these, but in the meantime for tonight, part of your assignment is to go back over these, check and correct. Now yesterday I did post as a PDF, not a solutions video, but I had all the answers to what I assigned Monday aside from the AP page 170 number 4. I will go over that later in the week. So if you have any questions over that, please let me know. All right, so last week we looked at the fundamental theorem of calculus, the part 2 of how to calculate or evaluate a definite integral. Now we're going to take a look at part 1. So if you look at this notation, carefully copy it down. Notice what's inside the parentheses is an integral, meaning the antiderivative, and then what are we doing on the outside? We're taking the derivative. So this is a way for us to see what happens when we take the derivative of the antiderivative. Now you would think they sound like inverse operations, right? You would think things would cancel out, and they will, but in a unique way. So we're going to go through this process. So again, we're going to let capital F represent the antiderivative of our function f of t. Then the integral from a to x of f of t dt. And I want to point something out here. This bottom limit of integration is going to be a constant. The top part is what's going to vary. So this is simply going to become the antiderivative evaluated at x minus, actually let me write this out first before I go to the evaluation part. This is going to be the antiderivative expression from x equals a, or t equals a to t equals x. So now this becomes capital F of x minus capital F of a, the antiderivative evaluated at x minus the antiderivative evaluated at a. Well, since a is a constant, this f of a is also a constant. So we did what was inside the parentheses. Now we're going to take the derivative of this result. So now we'll say the derivative of capital F of x minus capital F of a over dx. This will just become f of x, and then capital F of a is just a constant. And again, we can look at the derivative of the antiderivative is just going to leave us with the function. So if we go all the way back up to our problem here, the derivative of the antiderivative, you would think we would be left with f of t, but because we have to evaluate it from t equals a to t equals x, it's now just f of x. So it's f of, as long as this is a single variable, there's nothing else there, this is always just going to turn out to be f of x, f of whatever is up there. All right, so let's try it with this problem. All right, so we're taking the derivative of the integral from 4 to x of 1/2 t cubed dt. So again, the derivative of the antiderivative should cancel everything out, and we should just be left with our function evaluated. Instead of t, we have the x. And that's it. Now again, if we wanted to, we could start, this is just showing why we're able to do that. We start with the integral, take the antiderivative, so we're going to have 1/2 times t to the 4th over 4 from t goes from 4 to x. We could simplify this. We could just show it's t to the 4th over 8. Notice again the bottom number is a constant, the top part's a variable. So this becomes x to the 4th over 8 minus 4 to the 4th over 8. Now I want to find the derivative of this. So the derivative of the first term is going to become 4x cubed over 8. Derivative of the next term, because it's a constant, is 0. So this simplifies to just 1/2 x cubed. And there it is. Now you can always do the long part here, or we could just jump straight to that shortcut answer. All right, what we're going to take a look at next is off of page 287. It has a graph and several questions that we're going to take a look at here. So just copy the sketch of this graph down. We're going to use it to help us answer, I believe it's parts A through F. All right, pause the video if you need more time. All right, notice what's given here. It says, let h of x equal the integral from 0 to x of f of t dt, and then given the following graph. Notice this is the graph of y equals f of x, and we have an f of t up here. For part A, they want us to evaluate h of 0. So h of 0, x is 0, so now this just becomes the integral from 0 to 0 of f of t dt. Now, if this were any other number, we would have to do a little bit more, but because the limits of integration match, that was a property, wasn't it? So what will this turn out to be? Just 0. So part A was nice and easy. Let's take a look at B. On what interval or intervals is h increasing? Explain. So we're going to write out, we know a function is increasing when its derivative is positive, right? So now we need to figure this out. And that's what we're going back to part 1 of the theorem. So I'm going to say fundamental theorem of calculus, part 1. We would know that h prime of x, so the derivative of this antiderivative, if we follow that rule, it's going to cancel out. We're just left with our function f of, but in this case, x, which guess what? That's the graph. So this is huge right here. Writing this out can get you a point, maybe even sometimes 2 points on a free response question. Even writing this out, we want to explain in the least amount of words and symbols, and this is the best way to do it. So h of x is increasing when h prime of x is greater than 0. Well, h prime of x is equal to f of x. So when f of x is greater than 0. And where is f of x greater than 0? From 0 over to 6. Now we're going to include the 0, but we don't include the 6 because it's positive still when x is 0, but it's 0 when x is 6. So we could write it, can't believe I did that, x in the middle and a 0 over there. Or you could show interval notation with a parenthesis after the 6. All right, C, on what interval or intervals is h concave up? Explain. So we know h of x is concave up when our second derivative is positive. So if we go back and we know h prime of x is equal to f of x, that means h double prime of x would equal f prime of x. So a nice little connection there. So we are looking to see when f prime of x is greater than 0. Well, this equates to the what? Slope of the tangent lines. So from 0 over to 6, all of our tangent lines would have a negative slope. From 6 over to 10, they would still have a negative slope. rather 9. And then from 9 to 12, all of our tangent lines would have a positive slope. So this would be when x is, since 9 is the turning point there, we'll say greater than 9, and since 12 is an endpoint, so when x is greater than 9 and less than or equal to 12. Question D, is h of 12 positive or negative? Explain. So this is looking at h of 12 becomes the integral from 0 to 12 of f of t dt. Now, how can we relate this to the graph? We made one integral all the way from 0 over to 12, so we are looking for net area. So we're looking here, and we're looking here. We're looking for net area all the way from 0 to 12. So do you think we would have a net area, meaning do we have more area shaded above the x-axis? Do we have more area shaded below the x-axis? Or do you think they look pretty close to being even? It looks like we have more area shaded above, so that we would say this would be positive, since I'll call this area 1 and I'll call this area 2, since area 1 looks to be greater than our second area. We would expect this value to come out to be positive. All right, question E. Where does h achieve its maximum value? Explain. There's a couple ways to do this. So remember, h is our function. So we could say it this way, based on what we've looked at before. We know that h of x is at a max when h prime of x changes from positive to negative, or when h of x changes from increasing to decreasing. So these two mean the same thing. When h prime of x changes from positive to negative, that means h of x changes from increasing to decreasing. And again, even though we said it earlier on, we would want to rephrase that h prime of x is equal to f of x. So we could even put that up here. H prime of x, which is equal to f of x, changes from positive to negative. So we could read the graph here and say, well, f of x is positive from 0 to 6, and then at 6 it changes from positive to negative. So this is when x is equal to 6. Another way to look at this is in terms of area. But I like the first way because that matches the majority of what we were looking at throughout chapter 4. Or we could say h of x is at a max based on the most area here. So the most area occurs, the greatest area that we can attain here occurs at x equals 6. Think of net area. So h of x is equal to the area here, the net area, and it's at the highest when x is equal to 6. After that, we start taking that area away because the other area is below. So the most area occurs at x equals 6, then area starts to decrease. Again, because h of x is an integral, and then an integral is associated to area under a curve. All right, one more question. Where does h achieve its minimum value? Explain. Well, we're on a closed interval from 0 to 12. So let's kind of take a look at our points. We know, let's go back to h of 0. That was question A. We said that was 0, right? We know h of 6 is the max value. And we know h of 12 is positive. So it's not going to go below, because if h of 6 is the max value, we're not taking enough away to dip below a positive number. So this means Therefore, we have our smallest value, the minimum, h of x, is at a minimum at x equals 0. All right, here are the answers to the evens from what I assigned yesterday. These are posted as a separate PDF as well in Classroom today. I just want to point out, if our graph is concave up and we have a trapezoid here, like what we saw yesterday, it's going to be slim, but it's going to be an overestimate. But if our graph is concave down and we make a trapezoid, we're going to be a little bit below, kind of over-exaggerating that space between. So that's what's going to help explain those answers there. All right, so we are now officially finished with Chapter 5. I am going to give you some more, kind of more involved problems. They're more styled like the AP questions. So we'll be working on those for the next couple of days, and in the meantime, reviewing. So I'd like to make the Chapter 5 test next Tuesday. I might take a couple problems off from what I originally planned, but it's going to be around 45 to 50 points. Here are the types of questions you'll be expected to know. Approximate the area, so I am going to test you over the LRAM, RRAM, and MRAM. Sorry, I had to pause the video, but the first part is using the Riemann sums by hand. It could be an LRAM, an RRAM, and MRAM. I'm not going to make them too difficult because there's going to be part no calculator, part calculator. Trapezoidal rule by hand, graphically, and then integrals, use integrals to find exact area. So keep in mind the differences when I ask you to evaluate integrals versus where I want you to find the area. You also have to calculate percent error. So over here, evaluating definite integrals, maybe some indefinite as well. That's just what your quiz was over. That is where you don't put the square units. Finding the average value of a function and where this value occurs. Know the 5 rules for integrals. And then the big idea that we looked at today, the derivative of the antiderivative. And don't worry, we will be practicing this more over the next few days. All right, so today's assignment, these are more AP style questions. Please make sure you read the bottom half of page 278 several times. Let me know if you have any questions.